In section 1.3, we're going to be talking about set notation and, in particular, some special sets. To start off with the special number sets that we refer to, the first is the natural numbers. We're going to denote that with this double bar n. And the natural numbers are the numbers 0, 1, 2, 3, 4, 5, 6, and so forth. So it would be the positive integers, and 0 is considered the natural numbers. We also have another set of just positive integers denoted here by a double bar p. The difference between the positive integer set and the natural number set for us will be the positive integers doesn't include 0. For the integers, we denote that by double bar z, and it's going to be all the positive and negative integers and also 0. So numbers such as -4, -3, -2, -1, 0, 1, 2, 3, and 4 would be in the integer set. The rational number set will be denoted by the letter Q, and it stands for the set of all numbers of the form m over n, where m and n are integers, and n is not equal to 0. The real number set will be denoted by double bar r, and that'll include the set of both rational and irrational, which are numbers which are not rational. So collectively, irrational and rational numbers make up the real number set. For set notation in general, we use capital letters such as capital A, capital B, capital C, capital X, and so on to denote sets. And set elements are listed out inside of curly braces, such as the set A equal to the set containing elements 1, 2, and 3. Sets can contain any number, amount, type, or combination of discrete elements. They don't just have to be numbers within a set. Anything can be contained within a set discretely as different set elements. In general, we refer to elements contained within a set using lowercase letters such as lowercase a, b, c, x, and so on. These can be like variables to stand in for any element contained within a set, which again generally will be using the capital letters to stand for the set. We're going to use this notation, which looks something like an E, to denote when an element is part of a set. And similarly, we'll strike through that when we denote that an element is not within a set. So for example, we say 73 is an element of the natural number set, but -73 is not an element of the natural number set. Or we could, if we're looking at smaller sets, such as set A containing 1, 2, 3, and 4, then we can write 2 as an element of set A. We have another set notation for subset. This notation, for instance, if we had the sets containing set A containing 1, 2, and 3, and set B containing 1, 2, 3, 4, and 5, we'll use this notation to denote subset because set A is a subset of set B, since every element contained within A is contained also inside of B. So the set containing 1, 2, and 3 is a subset of the set containing 1, 2, 3, 4, and 5. Or we could just write A as a subset of B. On the other hand, consider these two sets, the set C containing 1, 2, and 6, and the set B as defined previously. In this case, C is not a subset of B, since all elements in C are not also contained inside of B. Some of them are, but there is one element that's not contained within B. So the set containing 1, 2, and 6 is not a subset of the set containing 1, 2, 3, 4, and 5. So the other set has to be entirely contained within the other for it to be a subset. So since 6 is not contained in B, we can just write C is not a subset of B. We also, in general, can say that any set is a subset of itself. So with the aforementioned set B, The set containing 1, 2, 3, 4, and 5 is a subset of the set containing 1, 2, 3, 4, and 5. So in general, for any set S, we say S is a subset of S. The set of just curly braces with nothing contained inside of it is a set containing no elements and is denoted with this symbol here, which looks like a circle or a zero with a line through it. This is called the empty set. Since the empty set is empty, we can say that an empty set is the subset of every set. So we say empty set subset of S for every set S. The elements in a set can be specified in general by using notation inside curly braces. It's particularly useful when the set contains infinitely many elements or a large number of elements that's hard to write out by hand. So for example, we can write sets in this form here. Sometimes this is referred to as set builder notation. This in curly braces, we have n colon, n element of the natural numbers, and n is even. This is read the set containing elements n such that n is in the natural numbers and n is even. So if we want to list out a few elements of this set, it would look something like 0, 2, 4, 6, 8, 10, 12, and dot, dot, dot from there because it keeps on going forever. So the set builder notation kind of states in words and in notation what elements are contained within the set. It defines the elements within the set. And we often will, for understanding what's in there, list out a few elements based off of the definition that we see. Here's another example. The set containing n squared such that n is an element of the natural numbers. This set will include each natural number raised to the second power, so starting with 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, and so on from there, or 0, 1, 4, 9, 16, and so forth. There's another set concept that's very important to discuss, and it's called the power set. This is defined as the set containing all subsets of a given set. For any set S, we denote the power set with P of S. So for example, let's consider the set V as the set containing A and B. And in other words, that means we have A and B as two distinct elements within the set V. We'll consider what sets constitute subsets of our set V. Well, first off, the set just containing the element A, sometimes called the singleton set containing A, is a subset of the set containing A and B, since it's entirely contained within the larger set. Also, the singleton set containing B is a subset of the set containing A and B. And as we stated before, a set is a subset of itself, so the set containing A and B is a subset of the set containing A and B. Also, the empty set is a subset of the set containing A and B. So what we have here are four different sets that are subsets of V. So when we write the power set for V, we write it as a set containing all of the different subsets. So P of V, the power set of V, will equal to the set containing the empty set, the singleton set containing A, the singleton set containing B, and the set containing A and B. Notice that power set is a set of sets. So I have double curly braces here to denote the larger set, the power set, and inside of it, each individual set has its own set of curly braces since they are our own distinct sets inside of the power set. And now we're going to look through a few examples of set builder notation and using the power set. Let's start off with this set defined by -1 to the n such that n is an element of the natural numbers. Okay, and so we'll list out the elements of this set based off of this definition. N is an element of the natural numbers, so we look at the natural numbers. Natural numbers start from 0, then go 1, 2, 3, 4, and so forth. So the set would contain -1 raised to the 0, -1 raised to the first, -1 raised to the second, -1 raised to the third, and ... from there, because it just keeps on going forever. So we could write this as the set containing 1, comma, -1, comma, 1, comma, -1, and so forth. Notice how the elements are repeating. -1 and 1 keep going on and on forever. That actually we can write this set as equal to just the set containing 1 and -1. Repeating elements within a set don't necessarily have to be written out more than once. It doesn't mean anything wrong if we do. It just means that a set containing, in this case, -1 and 1 is the same as writing those numbers out over and over again within the set. Okay, and the next set is defined by n element of the natural numbers such that 3 divides n. Recall this notation with the vertical line from the other section where it denotes divisibility. So what we're going to do here is list out the set containing elements from the natural number set that are divisible by 3. So if we go through the natural number set, 0 is divisible by 3, 3 is divisible by 3, same with 6, 9, 12, and so on and so forth from there. The next one is defined by the set containing all n within the natural number set such that 2 less than n less than 3. So can we think of an element in the natural number set which satisfies these conditions? Well, in fact, no element exists in the natural numbers that satisfies these conditions. Or in other words, no natural number is between 2 and 3, not including the numbers 2 and 3. So this set defined by these conditions would just be empty, so we call it the empty set. And we just use this notation to denote the fact that it's equal to the empty set. Another example here, all elements x contained within the real number set such that x squared is less than 0. Similarly, there are no numbers in real number set where the squared number is less than 0. Or in other words, no real number x satisfies x squared is less than 0. So this is another example of a set defined, which is the empty set. Let's go back to the notation for power set again. Here we're going to be doing the power set for set S with a variety of different elements inside of it. Okay, so the power set, if our set S is just equal to the empty set, the power set would be equal to actually just the set containing the empty set. Since the empty set is the only subset of the empty set. So again, when I list out the power set, I start with set notation, curly braces, and then on the inside of that I put the different subsets. In this case, there's just the one with the empty set inside curly braces. Now, on the other hand, if our set S would be equal to the singleton set containing A, then there are two subsets, and the power set would be equal to the set containing the empty set and the singleton set containing A. And this is because the empty set, again, is a subset of any set, so it's a subset of the set containing A, and also the other subset of the set containing A is just itself. So these are the only two subsets to put within the power set. Now, on the other hand, if the set S contains the set, or is equal to the set containing A, B, and C, we have more combinations to go through to find all the variety of subsets here. Okay, so if that's our set, then we have, let's go through the different possibilities here. First off, the empty set is a subset of, we'll just say here, S2. The set containing A is a subset of S3. The set containing B is a subset of S4. The singleton set containing C is a subset of S5. Or I have another one here. The set containing A and B is a subset of S. Another one would be the set containing A and C. That's contained within S, and so it's a subset of S. And then 7, we know that the set containing B and C, putting those two together inside this, a set would also make it a subset, since it's completely contained within S. And then finally, the set itself containing A, B, and C is a subset of S. So we have in total 1, 2, 3, 4, 5, 6, 7, and 8 different ways of putting together subsets for our set S. So what that means is the power set of S is equal to the set containing the empty set, the set containing A, the set containing B, the set containing C, the set containing A and B, the set containing A and C, the set containing B and C, and finally the set containing A, B, and C. So I've gone through and listed out each individual subset as a set individually inside of the larger collection called the power set of all subsets. Here we're going to look at the set of n from set A such that the max of n and 5 is equal to 5, where our set A is defined separately as the set of n in the natural numbers such that n is less than 22. Okay, so there's this max here that basically just means the maximum or the largest of the two numbers. So when we look at the two numbers contained within there, we'll take the largest of the two as the maximum. So let's start off with A. A itself, let's list out the elements of that set. It says the set of natural numbers such that n is less than or equal to 22. So it's going to be starting from 0, 1, 2, 3, and then it'll just keep on going all the way up to 20, and then finally up to 21. That's going to be the elements in set A. Okay, now if we look at the set of n, element of A, such that the max of n, 5 is equal to 5. We'll look through the numbers contained within A and compare them with the maximum with 5. So for instance, the max of starting with 0, 5 would be equal to 5. The maximum, we'll go to the next number in our set A, which is 1, 5. Well, that's still equal to 5. The maximum, the next number in set A would be 2 of 2, 5. Well, that's still equal to 5. The next number in our set A is 3. So the maximum of 3, 5 is still equal to 5. Set A continues to count up from 3 to 4. So the next one would be the maximum of 4, 5. That's still equal to 5. And then the maximum of the set, or the 5, 5, the next number up would be 5. That's still equal to 5. However, if we go up to the next number in set A, it goes from 5 to 6. So it'd be looking at the maximum of 6, 5, and that's equal to 6. And this is going to continue on from here all the way up to the last number in the set, which is 21. Maximum of 21 comma 5, well, that's going to be equal to 21. So only a few of these actually have a maximum of equal to 5. The rest of them are going to go beyond that, since the number is going to get bigger than 5. So the elements we're going to include are the 0, the 1, the 2, the 3, the 4, and the 5 will be within our set. So this set will contain the elements 0, 1, 2, 3, 4, and 5. Another concept we'll discuss because it generalizes ideas and uses set notation is alphabets, words, and languages in set notation. There's a very specific definition here using sets for alphabets. It says a finite, non-empty set denoted by here capital sigma, whose members are symbols, often called letters. That's how we'll define an alphabet. We're going to define a word as a finite string of letters from capital sigma. We denote with sigma star the set of all words using letters from sigma. And any subset of sigma star is defined to be a language. A word with no letters, also called the empty word or the null string, is denoted by this Greek letter lambda. So we'll consider words as strings of letters from any alphabet. We're going to use the letter sigma to stand for the alphabet set. And if a word contains no letters, we're going to use lambda to stand in for the empty or null string or null word. Let's break it down to a few examples here. First off, an example of an alphabet, which is fairly familiar, would just be from A to Z. So A, B, C, D, A to Z, sigma would be equal to the set of letters, and that would make up the alphabet. And now this could be any set of letters. It doesn't necessarily have to be A to Z, but in general, it could be anything. We're just going to look at this one as a specific example. An example of words would be putting any letters, any number of letters, as long as it's finite, of letters from A to Z together. So even just A, that would be a word. Even AZ, BB, ABBA, kind of nonsense or words that just don't really make too much sense, or words that do make sense, like math. That would be examples of words constructed from the alphabet set. Any word that can be constructed with letters from the alphabet will be made up into this set called sigma star. So sigma star will contain lambda, since that's the empty word, AZ, ABBA, math, anything you want to put together with a collection of letters from the sigma set would be contained within sigma star. Now, if we take any combination here and actually bring it down to a subset of sigma star, for instance, the English language would be considered a subset of sigma star, since it's a smaller set of words that we use in the English language. But in general, a sigma star can be thought of as any possible combination of letters. In this case, since we're using sigma as A to Z, sigma star would be set of any strings or words put together with those letters. To look at a few examples of alphabets and words and all this different notation involved with it, let's take a look at two different alphabet sets. We're going to make our alphabet sets fairly small. For the purposes of our example, we'll have one alphabet called sigma 1, will be the set containing A and B, and the other alphabet, sigma 2, will be containing the letters A, capital B, and B. Now, something to look out for very closely when we talk about alphabets is any symbol can be considered a single letter of our alphabet. So this, while kind of strange to think of it this way from the perspective of how we usually use letters in language, in general, the A capital B collectively can be thought of as a single letter within the alphabet set. So keep that in mind as we go through the next few examples. Now, first off, I'd like to look at just the sigma star 1. Now, the star means to stand for any possible word constructed of letters from sigma 1. So this goes on forever, but any sigma star will contain, first off, lambda, the null word or null string, and then other words that can be constructed from our alphabet would be words like A, B, AA, AB, BA, BB, and you could go on from there. You could have just like A, B, B, AA, and then it could just keep going on from there. So there are infinitely many combinations we can put together of our two-letter alphabet A and B to create different words. But sigma 1 star, I should say, will contain all the different words that can be constructed from the alphabet of A and B. Okay, and then on the other hand, if we look at sigma 2 star, words that can be constructed from the alphabet of sigma 2, well, lambda will be automatically included, and then single letter words would be A capital B. That is just a single letter word, but that's by definition of our alphabet. And so that's AB is one word, and then lowercase b is another single letter word. And then we could put together other words putting these together, such as A capital B lowercase b, or B A capital B. And we can put together all different variety of combinations, such as we could put together A capital B, lowercase b, just any combination of the two letters can be put together in different ways. And all of those would be contained within sigma 2 star. Okay, and then another few sets that we'll look at is the set of W in sigma star, we'll call it sigma 1 star, such that the length of W is equal to 2. Okay, and so how is this going to work? Well, I'm using lowercase w here to stand for any possible word. Okay, and so what this set will contain are just the words of length 2 with 2 letters. And if we look at the setup above, we can actually see the words that contain 2 letters. There's actually only 4 of them. AA, AB, BA, and BB are the 4 different ways of putting together the 2 letters here. So this set would be the set containing AA, AB, BA, or BB. Okie doke. So let's look at another example here using sigma star 2. And so we're going to use the other alphabet. And what this set is going to say is the set of words in sigma 2 star such that the length of the word is even. Okay, recall that sigma 2 is equal to the alphabet containing A capital B as a single letter and B. Okay, so the length being even means the length needs to be an even number such as 0, 2, 4, and so forth. We could make note over here that the length of lambda, which is again the empty word, is equal to 0. So that's important for this discussion in this set because 0 is an even number, so lambda has an even length. So this set would contain, first off, lambda. It would also contain words of 2 letters. So examples would be like A capital B, also A capital B lowercase b, B followed by A followed by capital B, BB. Okay, so these constitute length of the word being equal to 2. And then from there, it would continue with words of length 4, and so on. So like A, B, A, B, A, B, A, B, and then it just goes on from there. So this is an example of a set containing the words from this alphabet that have even length. Now, interval notation will come back here when we talk about sets. These are subsets of the real number set double bar R. Now, these are technically continuous, not necessarily always discrete, but they do involve set notation in some instances. So, for instance, the closed set, we call it, of A comma B would be the set of all x in the real number set such that A is less than or equal to x, less than or equal to B. So that would be the set with this particular look on the number line. And so we can have some other combinations here, such as what we call the open interval, which uses parentheses instead of brackets. The open interval of A comma B is equal to the set of all x in the real numbers, such that A is less than x, less than B. We can have the half closed, half open interval with the bracket A comma B parenthesis. That would be the set of all real numbers x, such that A is less than or equal to x, less than B. Or we can have the half open, half closed interval of parenthesis A comma B bracket, which is equal to all x in the real numbers, such that A less than x, less than equal to B. We can also have intervals such as bracket A comma infinity, and that's equal to the set of all x in the real numbers, such that A is less than or equal to x. And so you can see here the other variations with the parenthesis from A to infinity, or negative infinity to B with a bracket would be the set of all x in the real numbers, such that x is less than or equal to B. And similarly with a parenthesis, just not with the less than or equal to, but just strictly less than.